This is your screencast for the guided notes for Chapter 5, Ionic and Ionic Compounds, Section 1. This is Section 1. Today we're going to cover this worksheet, which is slides 1 through 23 of the slideshow. All these blanks you can fill in. You can fill in these blanks with the notes themselves, with just the presentation, or you can follow along with this slideshow, and I'll show you where all the blanks are. So here's our slideshow. So we're going to present this. So in Chapter 5, we talk about simple ions, ionic bonding and salts, and the names and formulas of ionic compounds. Today we're just going to talk about simple ions. So that's slide 1 through 23. So the objectives for today are to be able to relate the electron configuration of an atom to its chemical reactivity, determine an atom's number of valence electrons, and then use the octet rule to predict what stable ions the atom is likely to form, and then to explain why properties of ions differ from those of their parent atoms. When I say parent atoms, I'm talking about the atoms themselves, and then ions are when they gain or lose electrons. And so how much an element reacts depends upon the electron configuration. We didn't talk a lot about electron configuration because I only stressed the importance of valence electrons, and you'll see the valence electrons are the ones that actually matter. So the electron configuration, let's say, of oxygen is 1s2, 2s2, 2p2, 2p4, meaning that it has 2 electrons in its first energy level and then 6 electrons in its second energy level, and that's split up between s and p orbitals. S and p orbitals are not really vitally important for you to understand, and we're not going to talk about those specific electron configurations, but it's part of this slideshow, so I'm going to leave it in there and go over with you. So noble gases are the least reactive, meaning that they are in group 18 on your periodic table, or group 8A. They are helium, neon, argon, krypton, xenon, and radon. They are the unreactive elements of their row. And we're going to explore in this why they're unreactive. So the noble gases show almost no chemical reactivity because they have filled outer energy levels. The electron configuration can be written as S2P6, right? Because that's the 2 plus 6 equals 8. And 8 is the amount of valence electrons that they have. And so those 8 valence electrons don't actually make them stable. I'm going to talk later about what actually makes them stable, but it's convenient to think about it that way because that leads us to the octet rule. Octet meaning 8 electrons, and so if you have 8 electrons in your outermost energy level, you are considered to have the octet filled. And so here is a video that I found for you that explains the octet rule in about 4 minutes, and so you should watch it because it's nice. So here's a little drawing I made for you, talking about why noble gases are the most stable and why the octet rule is a real thing. So if we're looking at the third row on your periodic table, we have chlorine, we have argon, and then the next row down is potassium. So if you look at chlorine, which is number 17, has 17 electrons, and if you look and count them, there's 17 red dots there, and that represents the electrons. If you look at the outermost energy level of chlorine, there are 7 valence electrons, and the effective nuclear charge that those electrons feel is +7. So +7 is the pull that they feel for the nucleus, right? The attraction, because electrons are oppositely charged from protons, and there's 7 extra protons in the nucleus, and there are 7 electrons on the outside energy level. If you go to argon, argon's next. So 17 protons for chlorine, 18 protons for argon, and the electrons that are on the outside level feel a +8 effective nuclear charge because these guys feel 8 more charges than the innermost electrons cancel out from them. And so then if you go to the next one, you would think, okay, maybe the next one on the periodic table has a higher effective nuclear charge, right? The next one on the periodic table is potassium, number 19, and then you make another row, okay? And you make another layer of electrons. And so this electron on the outside layer only feels a +1 effective nuclear charge because there's 1 extra proton that isn't canceled out from all these electrons on the inside. So the ones on the outside are the ones that actually matter. They're the ones that do the chemical reacting. And so that's why the noble gases have the highest effective nuclear charge, and that's why noble gases are mostly unreactive. And so an atom whose outer s&p orbitals do not match the noble gas, they're going to react in a way that they lose or gain electrons so that they have 8 in their outermost energy level. And so if you have an element like potassium, potassium, when it reacts with water, gives up its electron and then reacts violently. I showed you a video of that, of me doing this reaction of putting potassium in water, and you see how violent the reaction is. And so, another example is calcium's not a halogen. I should fix that. So calcium, this isn't for calcium. This is for chlorine. Okay, I'll fix that. So valence electrons are the ones on the outside. And so if we're looking at elements, some elements from this row, right, if we look at sodium, sodium has 1 valence electron because he has 1 electron on the outside energy level. And if you have aluminum, aluminum has 3 electrons on the outside, right? He has 3 more electrons that are not in the inner energy levels, they're on the outside energy levels. And then phosphorus has 5. And so 5 valence electrons on the outside energy level. And if you look at your periodic table, this corresponds to that, right? And then chlorine, again, he has 7. So here's a cool video about how to figure out how many valence electrons an atom has. It's not terribly annoying, and he goes over some examples. So I think it's really great. You should watch it. And then, so this describes in addition how you can do that. So to find out how many valence electrons an atom has, you have to look at the periodic table. And so when you look at the column that they're in the periodic table, that tells you the number of valence electrons. So for example, hydrogen in group 1, they have 1 valence electron. Beryllium in group 2, they have 2 valence electrons. If you skip over the transition metals to the next column over, these guys have 3 valence electrons. Carbon's family has 4, nitrogen's family has 5, oxygen's family has 6, and fluorine's family has 7. And then if you go to group 18, the noble gases, they all have 8 valence electrons except for helium. So atoms don't have a charge, right, until they gain or lose electrons. And so that's the key to becoming an ion, is you have to gain or lose electrons. Okay? You can't do anything with a nucleus because the nucleus of an atom doesn't change ever. But the outside of the atom can change, and that's where the electrons are. And so you have an ion, that is an atom, radical, or molecule that has gained or lost more electrons. And so if you lose an electron, like potassium ion, that becomes a cation. And then here is a great video that describes how you can form an ion. And I really love this guy, he's really great. So you should watch this one. And then the other option you have, other than losing electrons, is to gain electrons. And that's what you see the nonmetals do on the right-hand side of the periodic table. And so here's an example of chlorine gaining an electron, becoming a chloride ion. When you become an atom with a negative charge, you become an anion. And so here's my beautiful illustration to help you remember what cations are and what anions are. So anions are negative because you see it's an ant that has a negative charge on him. And then cations are positive because, you know, you have cat and it has positively charged ions. And so that's how you remember. The cations are positive and anions are negative. And then, so both the atom and the ion have the same number of protons and neutrons, right? So that's what makes them the same. So the atom and its parent ion are the same in the number of protons and neutrons. But the electrons are what makes it different. And so in the example of calcium, this is actually calcium. Calcium gives up its last outermost electrons, these 2 electrons, and becomes a stable cation with a +2 charge. And when it does that, it looks like argon. It has the same amount of electrons as argon does. And argon is a very happy atom. And so here's how atoms form those ions to become stable, right? And it has listings of their electron configurations down here. Don't worry too much about that, but the charges you should know, because the charges help you determine how they're going to interact with each other, right? And you see that everybody in the same column has the same kind of charge and the same electron configuration. And then here's your transition metals. Transition metals are different. They form ions with more than one charge because they have the ability to lose more than one kind of electron and become stable. Okay, so we're not going to go into how that happens because it's very complicated. And so the important thing to know is that there are metals, namely the transition metals, that have more than one possible charge. And so it's important to note that atoms and ions are different in the way that they have different numbers of electrons, but the protons and neutrons are the same. So they have very different properties because they have different numbers of electrons. And so sodium and chlorine by themselves are terribly reactive, right? Sodium, you saw me throw it into water and it reacted violently, right? And chlorine gas is poisonous, right? It was used in World War I as a chemical warfare weapon. And so they're very nasty when they're by themselves. But when you combine them together and the electron is transferred from sodium to chlorine, you get sodium chloride. And sodium chloride, table salt, very stable. In fact, you use it to season your food. Okay, and so that's it. You should have all the things you need to be able to answer all of these blanks in here. So we have how much an element reacts depends on the electron configuration, right? The noble gases are found in group 18 of the periodic table show almost no chemical reactivity. This tendency to have empty outer energy levels or full energy levels of 8 electrons is called the octet rule. An atom whose outer s and p orbitals do not match the electron configurations of a noble gas will react to gain or lose electrons so that the outer orbitals will be full. The electrons in the outer energy level are known as valence electrons. To find out how many valence electrons an atom has, check the periodic table. An ion is an atom, radical, or molecule that has gained or lost one or more electrons and has a negative or positive charge. An ion with a positive charge is called a cation. An anion with a negative charge is called an anion. You'll recognize this illustration. And then not all stable ions have an electron configuration like those of the noble gases. Transition metals form ions without complete octets. Also, some elements, mostly transition metals, form stable ions with more than one possible charge. So having identical electron configurations does not mean that a sodium cation is a neon atom. Ions and their parent atoms have different properties. Nearly all metals form cations. The atoms of all nonmetals form anions. And to have a stable or have a noble gas configuration, an oxygen atom, for example, must either gain 2 electrons or lose 6. Acquiring 2 electrons requires less energy than losing 6, so oxygen forms oxide, the anion. And so here's some review questions. I want you to choose here whether valence electrons are in the inside or outside of the atom. The number of valence electrons can be determined by and I want you to fill in that blank on the periodic table. And in what way is the ion the same as its parent ion? An ion the same as its parent atom? In what ways are they different? What I want you to do is an ion has the same number of something and something as the atom, but has a different number of something else. Okay, so there you go. That's all you need to do part 1 of the guided notes.